Good evening, everyone. My name is Chandru Mirchandani. I'm the Programs Director of Incose, but just a little bit about myself. I have an electrical engineering degree from Rensselaer. Then I got a reliability engineering degree from Maryland and a systems engineering degree from George Washington. I've been dealing in systems all my life, from the tiniest system, which is a transistor, all the way to semiconductor devices, printed circuit boards, from chips to instruments to boards to integrated boards to systems. So as a result, I've been fascinated with this idea of going from seeing a system in a chip to seeing a system in the whole. So why did I start talking about cloud-based telemetry processing, right? So while I was at NASA for 15 years, we started processing telemetry data using mainframe computers. Basically, we were getting this telemetry data from the satellites being downloaded either through the deep space network and sent to us on tapes, and the download time or the downlink was very, very, very slow. As a result, it was easy for us to process the data, extract the information, send it out to the PIs, and it was not a difficult thing. Then the early 90s, we started saying that, more satellites are going to come into space, and more satellites, and the data rates are going to be well in excess of the 1 kilobit per second that we're getting. So we said, in about 10 years, we're going to have 20 megabytes per second, or 20 megabits per second. I said, okay, let's start building a system for that. And lo and behold, that system was not good enough. So then we went to the next system that was coming up, that was the EOS system. The EOS system was, we were sending up the Terra spacecraft. And again, we found out that we were going to get data coming down at 150 megabytes per second and 160 megabytes in hyperspectral imaging. And again, we started storing the data to the deep space network, sending it over to Goddard Space Flight Center, processing it. And we found that we're having we were at least 8 to 10 hours slow in our processing. So, and the idea was they were all being developed on a mission-by-mission basis. So when we had the systems earlier, we were having satellite data coming down from 4 different satellites. Each of those 4 different satellites, even though they came in custom frames of CCSDS frames, the data that was inside had to be reprocessed or extracted or processed using different algorithms. For example, MIT had some data coming down, and they were not going to give us the algorithms to process their data because the scientists were there, the PIs, wanted to have first dibs on it. Similarly, we had the Japanese having some instruments on it, we had the Germans having instruments on it, and all of them had different methods, different formats for it. So as a result, it became a mission on a mission-by-mission basis. So anytime I want to say, okay, we have another satellite going up, I have some bandwidth, how come I can't use this? Oh, we got to go through the whole process of putting on or piggybacking that software onto that system, and as a result, it was cost prohibitive, right? Scheduling differences entailed non-reuse. So there were schedule-driven development cycles. For example, if Jim had an instrument going up on a satellite and his schedule on his orbits differed from Mark's, then you say, yeah, we got to develop this. I can develop it at this time. Where is my development platform to do this? And what type of information am I going to use? What type of software am I going to use? So we did not have that. So we had large numbers of operational scenarios. So can we have a system at that time that could take satellite data from all these different formats, all the different varieties, all the different instrumentation, and say, yeah, we can do that. We can extract the information. We can process it. We can process it per instrument, per PI, and can have more than one instrument. But again, it became cost prohibitive, and we found that we had to have a lot more people working on it, a lot more instrumentation, a lot more platforms, a lot more software, a lot more hardware, right? So the reuse required extensive changes in software, hardware, and firmware to meet the mission needs. So we said new generation of processing modules and systems that can afford up to order of magnitude in cost. So basically what happened from the mainframes, we said, okay, now let's see if we can have a string of distributed systems that their only job is to take in 14 different streams of data with 14 different modules working separately and 14 different modules and do something which was consistent. Again, we found out this was again a very expensive process. So we went from this system, we say, okay, we know that one common processing element that's going on. Every single piece of data that comes through has to go through some frame synchronization, some deconvolution. It has to go through some error correction process. All that's consistent, all that's same. After that is done, it goes through different processing elements. But the processing elements are taking time. So we say, okay, what shall we do? The processing elements take time because we are doing the same option, same operation over and over again on this piece of data. So there's something that was compute intensive and something that was non-compute intensive. We say, let's take the compute intensive part of it and put it in an FPGA. And we found, we're getting a 17 to 18 times improvement in speed. So we went from the mainframes to systems that were like blades in a rack, for mainframes, we had distributor system to rack-mounted systems on cards. And then for each card, where each card was a processing element, to chips on a board, which ran on a Windows-based machine, which cost $150,000 to replicate, but which could process 2 streams of data at 160 megabits per second. And all that was because we went from from mainframe system into chips on a board. So I said, okay, but that's fine. How do we make it more flexible? So we have a process to do that. Now it's still a process of using that to our advantage with today's information systems, right? If you want to have a system like that at Goddard, a system like that in Japan, a system like that in Germany, you've got to have these applications put in, and they have the same old process coming in that they have to replicate. They have to replicate software, they replicate the hardware, they have to replicate things. So let's have something that can do this in a simple environment. So we said, let's use cloud, where we can have distributed software paradigms, but we have one element that has all the common parts that we need, right? So in keeping the industry to reduce infrastructure to minimal level and shared resources on cloud-based system. So one would turn around and say, but how can we do that, right? Then you realize that cloud-based systems can run on virtual machines, and virtual machines have lots of cores that can run separate operating systems on the same machine, right? So the massive server farms that Amazon users and massive server farms that all these Google users, they have a warehouse of information and data, but they manage to provide all that information, all that processing power to different elements. Now, could we harness that type of power to do telemetry processing? But telemetry processing, again, as I said, it has some unique things in it. But then I tell myself, yeah, but so has Amazon, so has the cloud-based system that Amazon is providing, both to AT&T, to Verizon, to the government, to the Department of Defense, to the FAA, to the Treasury. They're all specific things, right? So let's start, we can use that, right? But for having low cost, high availability, there have to be resource allocation and security protocols to be taken into place. So I told myself, okay, let's see if I can come up with some ideas on how we can use that effectively and still not break the bank, but give us cost-effective solutions to get what we want, in keeping either in addition to what's already there or to replace what's already there, right? So basically, adaptive nature allows you to do that, right? Now, modern telemetry and command acts as a gateway between the satellite and the ground, right? All they're doing is they're getting information from the satellite, processing it, giving it in the format that you want it, right? So how fast can we make this gateway, right? So to make this gateway as fast as possible, we're going to ensure security protocols are met. We still conserve all the data. If you ask any satellite manufacturer or any satellite user of satellite, he said, the most expensive thing for me is losing data. So the first part is the ingest part of it. I have to ingest all the data, right? So there's wide difference. So therefore, every time this data comes in, I say, okay, as long as it comes in a consistent common form, I can store it in an ingest format, and then I can start translating it like a translation, right? Just start thinking of Google translators. I say, wait, that's a translator. You're translating raw information into information in the format that each of y'all want it, right? So we have different encoding formats and transmit techniques used for uplink and downlink. Uplink and downlink, even though they use the same CCSDS format to send data across, and that was standardized across the world, not only in the US, they still use a different coding function to send their codes. Or else, if they don't do that, we can send a CCSDS command link to a satellite or to a satellite of a different country and could cause a problem. So therefore, on the satellite itself, they have these translators to get that back. So that's another case of complexity we have on using this type of system. All these things have to be tested to make sure that they work, right? So prior telemetry systems, the link with the mission operation computer through custom interfaces, specific to a given manufacturer, and it's different from mission to mission and very costly to maintain and upgrade. I remember when we were first working on my first system, which was called SPIF, or at NASA Goddard Space Flight Center, we had to use that specific interface from a specific manufacturer because they had all the specifications we needed. I said, why do that? If you're using standard protocol, you're using standard convolution algorithm, you're using a standard Reed-Solomon encoding or decoding algorithm, why don't we get it in its raw form and then do everything, any raw form? It's like a white box that we have today, right? Get in the raw form, we have all the intelligence to do everything else on the other side, right? So, for example, current systems used for NPOS, I'll show you the next slide. Science data is acquired by an orbiting satellite, is downlinked on a ground-based antenna, receiving analog signal transmitted to a single chassis solution of a hardware component, a software component, and the main elements are really the high-rate digital receiver system, which we built, return link processor subsystem, which we built, internal control system, which we built, and level 0 data product system, which basically takes a product and sends it out. So that's a basic element of the gateway. And if you look at it, right, so the proposed approach was to make this extensible, having these four different elements, and the system component, the interface, the science and data source via an antenna intermediate, and the user via high-speed data and communication network. Basically, what we're trying to do is we do the same thing, but all the intelligence to do all this processing comes from a central place. So I can use the same elements here, but I can tell us, okay, this is for this mission. I can repurpose it very fast. I can repurpose it very fast to use anything I want, or as long as I know where the input is coming and where the output is going to. And at the same time, I can also have the same virtual test bed to test it out, right? So from a resource perspective, the interface between the system and the data source is an external entity. Right? It's an external entity and cannot be sized or enhanced, but can be more efficiently utilized, right? From a service perspective, the system is envisaged as a number of service elements that are strategically distributed and flexibly architected so as to support one to many types of data sources and products. Basically, like the simple white box paradigm, I'm extracting the intelligence out into one area and say, this can do any system as long as I give it the right tools at any instant to do it, right? And that was the purpose I went through, right? So I said, okay, what are these elements? So I have an MNCS, which is a monitor. It monitors the service and interface system. It monitors everything, see how the things are running, right? I have monitors service elements state, the health of the service elements, controls and secures the data products. It identifies, isolates problem. It tells somebody, hey, there's a problem there, go fix it. There's a problem there, go fix it. Basically, what I'm trying to do is that I need to have a brain of the whole system that says, hey, there's something wrong. If there's something wrong, go and take. Otherwise, all the advantages of having something like this, of having something that can be used or reused many times, is of no purpose unless I can track and identify and isolate problem and ensure that these problems are sorted out and fixed in time. Now, the operational services that the MNC, the brain is looking at, can be broken out the ingest service, coordinator service, the processing service, and the output service. And why did I arrive at these names? Basically, it was from the whole paradigm that we had earlier. We had an ingest system or frame synchronizer. We had a Reed-Solomon system that does the error correction, we have the service process that does the service processing, and we have the data products distribution system. So we broke it down. I broke it down that the ingest system receives data from the antenna. It extracts it, synchronizes it, error checks it, and these are basically the top level objectives of that system. The top level object, the coordinator system, receives data, passes data, type of data, processing required, criticality, etc., etc. Processing service does this, and the output service does that, gives different output products. You may want an output product in a digital stream, or you want something encrypted and sent to you. I remember from the Terra mission, MIT had an instrument, and they said, any data you get from there, just take it out of the CCSTS frame because we don't know what is there. But my data, you just encrypt it, right? And put it on CD and send it to us registered post. I don't want you to look at it. That's PI, right? So you say, okay, we'll do it that way. So we could never find out if the system was bad, if the data was bad or good. We couldn't do it. We could do it at a link level to see whether there are any CRC errors or read Solomon errors, but not to see what the data was, right? So one architectural view was a replication of the small CSS, the small systems, to replicate them, right, all over the place, science data source, and through a WAN, you distribute it to the user. So users talk through a high cost, it's a wide area network where they can access all these different elements. I'm distributing these little boxes all over the place where they take the data, get the data from the satellite, process it, and send it out, and you can get it to the users, right? It's high cost and the complex configuration management of different suites of operational equipment. Because you may use, the iOS, Microsoft iOS, the Microsoft system. You may use an Apple system. You may use a digital Unix. You may use HP Unix. You may use different systems. And so you're trying to keep control through the WAN network. The WAN network, you can still extract it out and make sure that you can run it. But this is one option that they could use, right? So the second thing was, I said, okay, if I take the cloud-based options, right? Basically, what I'm doing is I'm abstracting all that into having that. I don't care what operating system you have or what devices you have. You're talking, as far as I'm concerned, you're talking through a white box whose characteristics I can change when needed, right? If you look at the basic white box philosophy that they're using now for software-defined networks, basically that's what they're doing, right? Because you have a network, you have a box, a Cisco box, you may have a box by Juniper, you may have a box that's 24 cards, you may have 48 cards. They say all these have different maintenance options. But if I have something that does the basic routing and the basic switching and all the intelligence is with me, I can switch from you to you whenever I want. I can switch from one card to the other card because I'm tracking all that information. All the maintenance is done in one area. And I can just go on replay. I can put 4 boxes there, cheap cost. I can have many, many more of them. Right? So the adaptive nature cloud-based is very flexible and fast. Virtual machines replicate actual fault and failure scenario from automated test environment. Basically, if I'm trying to figure out what type of failure modes or fault modes are there, I have a virtual machine, I can change it out. So one of my colleagues who I was working with, he was a software person, and he was very involved in doing virtualization of different operating environments to see how these different operating environments could detect the same fault. Now, that is something we are very interested in because if I'm trying to control different sets of equipment, different sets of SCSs that get data from the satellite, process it and send it out, it's important for me to figure out how can I simulate that environment? What type of information do I need to have? What type of faults and failures am I trying to identify, isolate, and fix? So as a result, those virtual machines replicate actual fault and failure scenarios. The Open Solaris test farm provides an open environment for virtual machines, right? Through a web-based interface, but they're limited in that capability. Basically, what Open Solaris does is it allows you to have, again, abstract out the test environment. Now, anyone who has used tools that do FPGA RTL logic, as soon as you do the RTL logic, you can build out a test suite to test out the digital string. And it's based purely on your input, outputs, and what type of patterns you want to look at. But they try to abstract out what really happens. All I want to know is, if I have this type of input, what type of output I'm going to get. So Solaris Farm tried to do that. But again, because they don't know every single permutation and combination, there's a fixed number of changes that they can look at, right? Cloud computing resources for software testing, specifically to simulate reality, load and stress testing, with the advantage of having available resources to do that. The minute we go to the cloud-based areas, we still change that out, but we can always go on adding more stuff into this area because we have the ability to go on adding new methods or new, should I say, new instances of different threads of space data that's coming through. And we're allowed to do that by using, and the idea is whenever you use these things, we're going to ensure that it really works. So how do we do that? We have to test it. And to test it takes time. Testing software takes a long, long time, right? So the proposed solution was virtualization and service-oriented architectures are made more available, right? The enterprise, either independent or within a space system organization, define a loosely coupled services running on agile, scalable infrastructure. Well, what do I mean by agile, scalable infrastructure? Agile means it can change very easily as soon as I want it. The more I can start doing some load balancing, for example, I can scale it up because it may be a blade-based thing, or I can put another processor with more cores in it. I can do some parallelization, right? And the service architecture, the service-oriented architecture, cloud can facilitate technology, have the ability to process large amounts of data as a service, and are both scalar flexible mathematical models correlating performance with network availability. Now, one might say, oh, I can go on adding more and more resources, but if your network can't handle it, it really doesn't work. So you have to have a model to say that how much loading you can have, and do I have to upgrade more of my network? Then again, I said, infrastructure is something you can add on, right? Now, if you go and talk to AT&T or Verizon or any of these big network people who do all these backbones all over the place, they say, they have only 2 cores all over the US, 2 or 3 cores maximum. These huge virtual cores do all the load balancing. I said, but how big are these cores? They're big enough. And how do you do it? He said, well, we have local areas that we send the data off to whenever we can, and we start moving things around. Now, if these guys who are handling over 300 million, only in the US, 300 million people, which is, you multiply that by a factor of 1,000, which is the number of interactions they have in every second, we figure out that from a cloud-based process, you can do it. So I asked a guy from AT&T, so how do you handle this? Oh, we have cloud-based architectures to handle our resources. We have models that handle our resources. We have models that dynamically adapt, right, to these network flows to do that. I said, if we can use those same type of models in adjusting our flows, here we're handling a whole bunch of spacecraft, we can do the exact same thing, right? So this was the architecture I came up with, right? It's in the cloud. We have various sources coming and various sources going out. We can go on changing them, and because these satellites don't come in at the same time, we can have various numbers, and we can make this as many as we want, up to, we can go and make it big as we want, as soon as you, and the only point is that you got to realize, you got to make each one of them from a data point of view, they got to make sure you got to isolate them from each other. So you start saying, oh, do I have to do some partitioning? Yeah, you may have to do partitioning. Another question I asked of the network guy, I said, how do you partition data that you're sending to the 3-letter agencies as opposed to the people, the public? He said, oh, we have partitioned area that people can't cross over. These partitioned areas are partitioned areas, you can't touch them. And oh, by the way, when emergencies occur, they can hop over and take anything you want, but you can't hop over in at that site, right? I said, oh, that's great. We want emergency people to be able to talk when there's emergency to talk to us. So there are ways of doing that, right? Now, I'm not saying it's cheap, I'm not saying it's easy, but it can be done. So a set of ingest instances running with IS based on the adapted or preset values. You preset the values of what you want. I know the satellite, you come and preset it, it's going to do this. This satellite is going to use this, right? The coordinator system extracts the packets and the processing function needs for the data system. will decode, output system will do what it wants. The data delivery is monitored by the monitor and control system, say that, hey, Jim's satellite data is coming through, it has to go to these people, let's say that's done, it's going to take 15 minutes, okay, the next one is coming around, I'm going to balance it, okay, I don't have that, there's another satellite coming in, I can go on handling that, and at every instant, I have a different set of software modules coming in, a different set of operating systems coming in, a different set of resources that are needed for that instance, right? To create the data, to create the output, to create the different types of, should I say, decryption algorithms, different type of packaging. For every instance, I can have it because I have the power to do that because I can have virtual machines running on this side. I don't have to have it on that end of it, right? So the extensible architecture, I can go on adding things. I can go on increasing the coordinating system. I can add the more ingesting system. I can add more output system. And because it's not going to be, now, one would say that I'm not going to have this room, and then I say, I can't put any more in this area, I've got to build another room. So the idea is you got to, the selection of this area, of this system has to be, carefully selected, put it that way. Now, if you look at the NASA Space Flight Center, NASA administration, all their science data is processed at Goddard Space Flight Center. All the shuttle data for command and control is processed at Johnson Space Flight Center. Some of the deep space network stuff is done at JPL, right? Alabama and California have some NASA center that do specific things, basically do the atmospheric stuff, right? Now, they have distributed their different functionality to different centers. You could do that. So you say that this is for science telemetry processing, this is for, health, weather data processing, you could do that, right? So you may say that, so I don't have one cloud-based system, I have a couple of cloud-based systems depending on the variety of the different elements that you're trying to change, right? So, as I said, startup costs are going to be high. Like building the hardware, software, flexibility to support more missions, right? The virtual process allows flexibility of horizontal scalability to accommodate new missions. We have that. Right? The service functions allow basic telemetry processing to be a common element, customization envelope to be added with differently scaled resources for each mission. Right? So if you're getting hyperspectral images, right, like we had from EO1, they were different from the information we were getting from Terra. Terra was sending us data on how the ground-based moisture patterns exist over Nebraska and the Midwest to help the farmers know when to plant and what the periodicity of the water is going to be. Whereas the hyperspectral images you're getting on from EO1 were telling us that hyperspectral ozone layers over the Earth, which are completely different and they're used for different elements. So so the amount of processing and the number of envelopes on that data were a lot more. Right? The way you extracted it, was it a pure processing element, or you take it down in strips and then add it up? So the sizing the system takes into account life cycle time for hardware processors and permit seamless enhancement to next generation. So as with all hardware, and therefore albeit software, there is an end of life. So hardware is moving on with time. We are getting from 2.8 gigahertz processors to 14 gigahertz processors. We're going from 12 cores to 24 cores. I'm working on a system now, we have 48 cores. So why do we need that? We really don't want to overdo it, we don't want to underdo it, but still there is a time that we're going to take this into account. And if you have a system that has a lot of complication, it's going to take a lot of time, and a lot of time means a lot of risk, right? So, if the system has to support, so this is a use case I just took as an example to test it out to see, hey, is it really worth it or not? Right? So a system will support 20 missions would have 16 orbits per day, every 90 minutes telemetry downlinks from 10 to 20 minutes. Traditional system would not be able to handle 20 missions concurrently. They can't handle all 20 comments, they have to handle one, they're all shifted in time, right? A somewhat sequential manner. If mission has the same downlink pattern but could be asynchronously ingested, that could be an overlap, right? A low option for telemetry processing, replication of system allowed simultaneous downlinks to be ingested and processed. We can go and have, okay, let's have, because we can't do that, let's have a separate system to do things, right? So I say, consider supporting a mission every 90 minutes. I said, I calculate out the number of missions, multiple of 16, and I figure out what the option, traditional systems, SCS, or the CBS. CBS is the cloud-based system. And I figured out how much it can do, right? For concurrent support, system instances, and cost of the support system. So I did this, the paper gives all these calculations. I really don't want to go into the calculation part of it. And so I assumed a growth factor of missions per year and worked out the cost of reconfiguring all these systems based on the new missions coming in, cost per mission per system, and replacement upgrade cost per system. So I put all these in to see that, not to sort of say that, hey, not to compare apples and oranges. I said, bring it down to the same common denominator. Said everything has a cost. And that cost is in terms of schedule, people, and what the equipment you have to change. So the traditional distributed system, multiprocessor, 4 CPUs, support more mission, etc. Time to configure has to be less than 15 minutes of the next set of 4 missions. Because I'm trying to make sure that every time that we have more missions coming in. And the total number of missions the traditional system can handle is 8, assuming that all of them have an orbit of 90 minutes, right? This is based on information I had when I was working at NASA. So reliability and performance. Traditional system have a high-end multiprocessor workstation, independently fail, bring down the telemetry processing center, right? So SCS system is more robust because it has an operational string specifically, so if you break, only one part of it fails. So I don't have one common element of doing it, you have common like swim streams of their own. The CBS system is a hybrid solution between these two systems. It has a medium that can have a lot of reliability, a lot of redundancies here, and I can have a whole bunch of redundancies by having load balancing through my hardware elements, right? So I said, I compare the alternatives, the traditional processing system, the SCS processing system, and the CBS processing systems, the different type of telemetry processing systems that we're working with, right? And I came up with the results, right? What the relative costs were, and so since it was not fair for me to say, oh, it costs so much, I just took it from number of CPUs and multiplied it by that and tried to figure out to bring it down to a common denominator, right? And upgraded after how many missions, how many CPUs, etc. And I worked out what the performance I need, what performance it should need, what relative cost is, and what the relative cost is for 256 for 32, right? So that was a result I had from an option that I figured out is common based on last time I worked at NASA, right? So where do I go from here? What do I do? So I got to make sure that the data is more secure. That's something that is very, 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 very important. Especially if the data I'm downlinking is from a satellite that's giving, for example, information on the traffic system in the US. You can get data for that, right? I know that the roads work that's going on in Arizona and Florida, tracking using planes to track traffic, patterns and give alternate routes to people to drive, right, could be done far more effectively if you have satellite with high performance, actually fast turnarounds. The planes travel, they still have to that's great, but you really don't want that information to be given to people who can misuse it for bad purposes, right? So there's secure elements have to come in. Or you don't want to give it to people who can use, hey, for a prank, I'm going to get all these guys to go this way instead of going that way. So that security issues do come in there, right? The propensity for system failures, especially software, increases added complexity to processing algorithm. As it says, higher complexity can cause either complexity of system of systems or complexity of all the modules in one system. That 2 levels of complexity. If you use McCabe's complexity rule, you can figure out what you need to do based on interfaces or non-interfaces, right? Case studies are agile fixed test operate processes are being quantitatively evaluated. People turn around and tell me that agile is the best way to go. And I tell them, agile is a good way to go as long as you do due diligence on what you're testing and what your results are. I can test a piece of software very fast and say, hey, it really works, it really works, it really works. Now, let me test this piece of software, it works, it works, it works. Now, let me test a piece of software together. Does it work, does it work, does it work? And so a lot of people, I hate saying it, but hardware as well as software, they work in their cocoon and say, my thing works really well. And so the agile part of it is good, but you've got to make sure that the fixed test operate processes are being correctly. Cost impacts related to the agility of the process are being quantified. So The faster I make something, the faster I do something, the faster I make a change, the faster I correct something, it still comes with a cost, right? You still got to test it. If you don't test it, you pay for it later on down the line. So where is the break-even point, right? So I'm coming up with a model to see what should be done, and should it be manual, should it be human, or should it be automated? How much credence can we give on the human element? How much credence can we give on the automated element, right? So questioning point was the new thing that's coming out on the 737. So should automation have been there or not? Should the human be allowed to override or not, right? Now, you get two schools of thought. One school of thought says, no, they should have allowed to override. The other school of thought says, well, if the person didn't take action in the right amount of time, he was a goner. But, you have got to tell yourself that a pilot should be able to do that. Then they say, yeah, but all pilots are not the same. It's like all humans are not the same. So that becomes a very political thing and very, subjective. So what I said and done, those things have to be taken into account, right? And you have got to say worst case, best case is the best way to do it. And so the agility of the process I have to see how fast I respond to something, how quickly we do something. Is it really the way to go, right? So the future research that I'm doing is it cost effective for testing? We're talking about this, but you can't install a system, you can't install a process, you can't install a mission unless you have tested it, right? And that gives you the proof of the pudding. So how reusable are the resources? Can they really be used? Can they really be reconfigured? I'm talking about, hey, I can put, if I talk the talk that the vendors talk, oh, my system is very, extensible. I can put 14 blades there. I can put 17 blades there. I can have multiprocessor. I can just take one and drop it in. I take another one and drop it in. Is it really so, right? Is the test bench option feasible? Can I do it with small footprint, or do I have to need all these elements from all over the place? Or do I focus it in this area alone, right? Can it support many testers, right? A tester has to have access to the resources to test it effectively. You can't say, well, I'll give it to you tomorrow. If this is going to be effective, the tester should be able to do any test at any time. Today, when we do testing at the place I work, we have a certain number of test benches and test labs, right? And the people who want to test, they have got to book time in advance. Okay, I got the 6 a.m. to 12 shift. Then I got the 12 midnight to 6 a.m. shift. And they work through the night because we have a fixed amount of test benches to work at, right? So if it can't, can it support cloud-based internal web networks? Can we test remotely? Some things you can, some things you can't, right? Could cloud servers provide all the data sources and configurations? Can we have a common set of redundant routers? Yeah, maybe we can have common set of redundant routers. If you go away from the specific, I want Cisco 4500 or I want Juniper 2200 or such as, hey, no, I don't care. I want the characteristics of this. I want the characteristics. Why do you want this one? Because it has the 48 port. It does 4 protocols. It can have 2 inputs, 2 outputs. I want it for this specific reason. Hey, I'll take a white box, small white box, big white box, the bigger white box, the biggest white box, and give you all the options where I can reconfigure them on the fly for the number of ports you want, for the number of protocols you're handling, for the number of things you're going to do, right? So these are things that you've got to still answer before you say, yeah, this is the best way to go. So one of the things that I'm looking at is using software-defined networks to be system agnostic. The minute you use software-defined networks, you're basically telling yourself, I don't have to have a Cisco. I don't have to have this. I don't have to have that. I can redefine these things. I can adapt them on the fly using my system. And I'm done. I talk very fast. Questions?
Chandru, have you looked at any commercial cloud providers? Amazon has a ground station service, so does Azure.
I have read their stuff. I haven't talked to them in person. And I got to be very careful when I talk to them about these things because they say, oh, is there a project y'all are doing? Can I come and see you? So I got to be very careful. So I have to wear my GW hat when I talk to them. But I have read what they've written. I've asked for papers. So at conferences, people talk about these things, and I ask for papers, and I get them down or download them.
Some of the areas for scalability,
Mm-hmm.
some of the issues that you mentioned, they probably ended up pretty well.
Oh, yeah. We are using Amazon Cloud for some of the work we are doing on 2 different projects. But the thing is, we are just using a part of that total suite of processes they can give us. And the reason we are doing it is we are going to ensure that our customer is happy with it. And some of the information that we pass along is, quote unquote, supposed to be secure. Not secret, but secure. Question?
Over here.
Yeah.
Thanks. There's a lot of good information. Did you, and I'm not sure of the entirety of the thing, but did you, one of the big factors in decision making is risk. And when you have alternatives, there's always different kinds of risks associated with that as a decision. Is that something you're going to do, or have you looked at that? Or?
That's what I was going to do. As I said, the other thing is it. So for me, you can buy down risk, right, by testing your stuff. And you test your stuff by having every single option, every single alternative. So my argument is, can I simulate every single option to ensure I can buy down risk, right? Today, we have a fixed system that we do. We try to identify failure mode. They say, well, this is a failure mode. There's a likelihood of it, and this is a hazard consequence. So I'm going to buy it down by either reducing the likelihood or decreasing the consequence, and decreasing the consequence by putting in mitigation strategies. So I'm saying I want to make sure that I can do this. I can test this out. If you're doing it on a defined set of systems, you can easily handle it. But if you're doing something that you're abstracting yourself, you got to be careful that you can test those simulations. So that's one of the things I got to say. Is it really workable from a risk point of view?
Right, and there's a lot of like operational security risks. There's all kind of other type risks right in there too, which are, I would guessing, is a huge amount. And that's why I think that's probably, would you agree, that's really important in an analysis like that. Those total key risks are a key thing in looking at it.
That's a good point. I should look more into that. Yeah.
Question. Maybe it's you ran into major problems in Incose and DNSP. Applying similar orders at the time purposely to produce tools on board. We've got a big improvement. We upgraded to fiber this fall. But we're still limited in terms of how much we can take down at any point in time. And normally, as soon as it's sight from the satellite, until it goes out of sight, we're up in data almost 100% of that time. And then the next one is coming up and back on a time basis. Now, part of the problem I see is that one problem is we don't have enough dishes and not likely to get them anytime soon to be able to handle the backlogs. Number 2, we go into a pre-processing. Parts of it go where they launch to, parts of it go into target routines. At the same time, and parts of it get launched after, because there's a little bit of purification that goes on as you staff. If I look at the diagram each you have, it strikes me that the possibility is that you need more units to replicate Tampa ready to be able to handle those kind of data.
Right. Because I said that it should be adaptable for different source and data type of structures. We should also be able to have different types of processing elements. So you could have the asynchronous part of it if both of these have to come at the same time. That's what I'm trying to say, right? That when one goes out and the other one is coming in, but you need both sets of data to get your output product, correct?
Yes. But, okay, now I'm going to take it wrong. If we begin to transition more so than we have, to smaller satellites, which have higher data rate capability, but less overall capability for the spectrum of data that they used to be able to take from one satellite.
Right.
Okay. And we're going to be flying different orbits at different times.
So you're talking about a constellation of them? A constellation of them giving the same. Okay, that's what the British do. The CubeSats that they do, they have a set of them running, right, where they get different parts of the data coming from different satellites. That's one way of doing it.
When they come over the horizon.
Right. Mm-hmm.
As soon as they hit something like Svalbard, that's the biggest one we have right now.
Yeah.
I'm not aware of any plans that are realistic with an increase
Svalbard, no.
in capacity and capability.
Mm-hmm.
Okay, and if you increase what's coming with the smaller satellites, we get getting different data, but it's a high data rates and highly refined data that's going to be sent down to the same dish.
Okay, so you're having a resource problem where your receiver is concerned, really.
The problem is compounded is that the total amount of data coming down is probably going to be the equivalent of approaching 2 times what we're handling now with 1 second.
Okay. That's an interesting problem.
He wants me to talk through this.
Well, everybody else was here. Yeah, that's interesting problem.
Okay.
Yeah. I should look at that and see how that impacts this. Could be something that we've got.
It's going to be slowly implemented. I'm looking at this as being a probable problem.
Mhm.
The progression has gone in the last couple years in particular, okay? And I don't know how to overcome those particular areas where we're going to be constrained by capacity, particularly capacity over fiber.
So let me ask you a question. So the original installation or deployment of that dish was for a specific load?
Yes.
Yeah. So how can you repurpose it to have more excess or to handle the extra load that's coming in and still not?
The probability is high that we'd have, in order to add another dish, we might have to move the existing one in order to make enough room for having another dish so they didn't have too much interference, number one. Number two, in terms of the data capacity, it's likely to exceed the existing fiber capacity and probably have to put in another line.
Oh, God, yeah. And Svalbard is not the best place to do it in.
Not right, likely. I mean, it's stuck up there. Well, we're slowly keeping it out of snow and ice on part of the season, which never happened before.
Mm-hmm.
Okay. Some people call it global warming, but
I've been up to Tromsø, so.
yeah. Okay.
Yeah.
Thank you.
Everything what you talked about
Mhm.
has to do with the capacity of the downlink and the ability to go from the gateway to the processor.
Right.
But it seems that if there is existing capacity from the gateway to the ground station, there might be already pre-planned dark fiber that would absorb the extra data rate coming down. If you could actually
If you, that's
expand the
that's
capacity of
asking.
the downlink.
When you deploy it, when you size it initially, what was it supposed to be sized for? But he said it's something new that came online, right? So then you are changing resources that are on the ground.
Right. I have a question. There was a slide where you talked about continuing work just before your future research slide, and you mentioned protocol vulnerability and data security. How do those two terms differ?
Well, let me get that. Yeah. So when I say how can I make my data more secure is that my data is coming down, and if I'm sending from point A to point B from a specific area, how do I ensure that it is secure? For example, today, on some of the systems I work on, they said that you have to have 3 or 4 layers of protection before people can access the data or see it, right? I'm looking at it from that point of view, right? Now, the second thing is, if I'm using common protocols, for example, the one option we had earlier, instead of using CCSDS links to download data, let's just use TCP/IP protocols, regular, and say, wait a second, how can we ensure that that is good enough? So So my argument was, CCSDS is a space data communication link we use, and we build in, we encrypt the data and send it down. We could do the exact same thing and have a TCP/IP envelope right on top. So it becomes, you have a lot more overhead on a little bit of data. Now, so that sort of goes counterintuitive, that you're really reducing the performance, right? So maybe, is that a way of doing something without all this overhead added on, encrypting and decrypting and encrypting? Can we compress data, encrypt it? There's an extra process going on. Do we do it on the instrumentation on space, or after it comes down? Those are the things I'm looking at, some of the stuff I'm looking at. Yeah. Okay, thank you very much.